Solve some first order homogeneous linear PDEs with constant coefficients. Okay, so guys, consider the differential equation a partial of u with respect x plus b partial of u with respect y equals 0, where of course a is not equal to 0 and also b cannot be equal to 0. Otherwise, well, no equation, right? So the solution, as you can see, is very boring here. It's just some function of bx minus ay. That's all it is. But the question here, how do we get this solution? Well, although we can solve this equation using separation of variables, I mean, it's you look at the form. I'm going to take a different approach. Okay, let me show you the derivation of the solution. That's why I asked you to watch the video on the chain rule for calculus 3 because we're going to use it today. Okay, so of solution for this is what we call a change of coordinates. And you guys have done a bunch of change of coordinates, especially in Cal 2 and Cal 3, changing to like, what was that, polar coordinates, cylindrical coordinates, spherical coordinates. Well, there are many coordinates out there, not just those three. So the change of coordinates that I'm going to do here is to let the solution some function of u of x, y, or u of xt. It could be u of xt, another variable, another set of variables. But we're going to do u of xy for simplicity. I'm going to call it another function v. That's the change of variables. And I'm going to introduce a new variable. That's the Greek letter c. All right. I'm not sure if that's a correct pronunciation of the of the letter. Okay. And well, where in this case c is equal to bx minus ay. Notice something interesting here, and let me highlight that. Notice how the y remains constant. Doesn't change in this new coordinate system that we're going to introduce, okay? Well, so because we have a new function that depends on z and also y, which doesn't change, that means we need to change the partial of the solution of the solution u with respect x and the partial of u with respect y using the chain rule. So in this case, what happens? So taking the partial of u with respect x, that is taking the partial derivative of v with respect z, and times the derivative of z with respect x. All right, so here the partial derivative of v, which we don't know what it is, that's simply v, okay? And I'm going to do a subscript. That's also kind of a hard letter to write. It's a kind of, I mean, you can use any letter. However, literature uses this letter to represent this change of coordinates. And well, what is the derivative of the z equation with respect x? Okay, take the derivative of that equation of that function rather with respect x. Isn't that going to be b? Okay, so that times b plus v with respect y in this case. Okay, times what's the derivative of y with respect to x? Guys, this could be the tricky part of the problem because again, what did we say about y? Didn't we say it's constant? It doesn't change. So if you differentiate y with respect x with respect whatever variable, doesn't matter because it's constant, it's going to be 0. So that's going to leave us with v times v with respect z. You can make like a little tail down there, all right, to make it look like cool. All right, what about the partial of u with respect y? So I'm going to differentiate v with respect z, which is again v with respect z, times the derivative of z with respect y. But isn't that in this case negative a? Okay, plus v with respect y. But what is the partial of y with respect y? Partial y with respect y, doesn't that reduce to 1? Right? So times 1, that equals negative a v with, with respect z plus v with respect y. What am I going to do here? I'm going to substitute these two back into the original equation. So this guy, let me highlight this guy, which is partial of u with respect y, which is this term. Okay, that's going to go here. And this term, which is partial of u. Oh, wait, that goes here, and that goes there. All right, so that means that's going to leave us with, what is that? A times the quantity in green, which is B, V with respect Z, plus B times negative A, V with respect Z, minus V with respect Y. That equal to 0. So let's clean up the equation. That'll be AB, V with respect Z, the Greek letter Z, okay, plus, or actually minus AB, V with respect Z, minus B, Vy, V with respect Y, all right? And that equals to 0, okay? Do you see how the first two terms cancel, right? The first two terms cancel, and that leaves us with only negative b, v with respect to y equals to 0. And guys, notice this equation is not, even though, well, it's involving some partial derivative, but there are no other partial derivatives. So you can think of this as simply what? Just an ordinary differential equation. I'm going to divide both sides by negative b. That's v sub y equals to 0. So that's dv dy equals to 0. Now, separating the variables, dv equals to 0 times dy. Integrate both sides. So that's v equals to, what is that? V equals to 0y plus c, where in this case, guys, here we need to go back to our initial setting. What is v anyway? Isn't that a function of z and y? Okay, which is some constant c. But guys, didn't we integrate with respect y? Because this is a function of two variables, this constant right here should be a function of the other variable that was held constant. In this case, z. Okay? So now let's go back to our original substitution. Okay, what is v of cy? Isn't that our u of xy, really? And what is c? By back substituting, this is not c. I'm going to call it some function f of bx minus ay. And that's how we get the general solution. All right? So that's the proof or derivation, however you want to call this. All right? That's the end of it. Okay, how do we solve some examples here? All right. Well, so have a look at, we're going to do a couple of examples. So solving the equation to partial of u with respect x equals to partial of u with respect y. Let that be equal to 0, subject to the condition u of 0, y equals to cosine of y. Then I will also show you the graphic representation of this, which is a pretty cool thing to see, right? You'll see. Okay, so number one, in this case, all you need to identify that A equals to 2 and B equals to 1, where in this case, the solution will be a function u of x, y, which is a function of x, of ax, bx minus ay. So u of x, y equals to f, some function of x minus 2y. All right? Actually, that's the general solution to the differential equation, guy. That's it, right? That's all. But that's just the general solution. We want the particular solution subject to that condition, u of 0y. Okay, let's apply that. So with u of 0y, what does that mean? Replace with x equals 0 to this generic function that is f of 0 minus 2y. Okay, and what do we do? That equals, okay, substitute this into, isn't that equal to simply f of negative 2y? Okay. And guys, uh, what is u of 0y equal to? Isn't that equal to cosine y? Okay, cosine y. So we're almost there getting the particular solution. Okay, guys, let's work with this equation. I don't like this f of negative 2y. I'm going to turn it into an f of y. So what are we going to do here? Divide every instance of y in our equation here by negative 2. All right? That'll be simply f of y equals to cosine of negative y over 2. Or negative 1/2 of y. Doesn't matter. Right? Let me do negative 1/2. I think it's better. But well, what do we know about the parity of cosine? Isn't that a what's it called? An even function. So cosine of a negative is cosine of the same angle, positive, right? And well, that's f of y. How do we get the particular solution finally? Okay, check this out, guys. Isn't the solution to the equation a function of bx minus ay? All right. So replace every instance of y with bx minus ay, right? So f of, well, not bx, I mean the actual form, the x minus 2y instead, okay? So that equals to x minus 2y equals to cosine of 1/2 x minus 2y, okay? And you might want to reduce. This is cosine of 1/2 x minus y. And that is the actual solution. Now you may go ahead and call it u of x y finally equals to this function here. And that is final answer, right? So what is this about? You're considering the form, which is kind of weird form of the solution, apply the condition, play with the equation so that you just have only one variable with no coefficients or no signs, and then do the shifting in accordance to the substitution here. Okay, guys, now if you're wondering what the hell are we doing here, let me show you a graphic representation. Okay, so all right, so here in GeoGebra, we have a graphic representation of what this looks like. Maybe dim the lights a little bit. So, well, number one, do you see this curve right here in blue? That is actually a function of y and z, essentially. Well, this z technically is our u variable, but I didn't change the label, which is the cosine function. Yeah? So that is when x equals 0, so see, this is the x-axis, this is the y-axis. So that curve only travels, or that wave only travels along the y-axis because x equals to 0, isn't it? Now, what about the general solution to the PDE? Okay, so wasn't that cosine of 1/2 x minus y? Let's have a look at that surface. That's actually a surface. And that is a surface. Now, notice how there's kind of a diagonal. It's not it's the ups and downs on the surface are not aligned along the x-axis or the y-axis. Can you see that? So they're aligned. I mean, let me do a better perspective. Okay, x-axis, y-axis, but look at the maximum points on the function. Do you see how they are aligned on like a diagonal line? I'll show you what it is in a minute. Okay, so here's the thing. Um, what should I do first? Okay, let me show you this curve. So actually, let me drag that solution. So what if instead of saying u of 0 y equals to cosine of y, I say u of 1 y equals to cosine, or u of 2 equals to cosine, or u of 3, or u of negative 1 y, or u of negative 2 y, etc. Well, actually, that same cosine function, check what's going to happen. Let me drag it to positives. It's going to be dragged along the surface. But wait, there has to be like a fixed set of points in there that controls that dragging of the curves. That's actually this curve right here, right? That's this curve right here. There's another curve right here. There's another curve right there. Do you see how those curves are on the maximum points of the surface? All right. Okay, there's more. I believe, yeah. So, okay. So that's the solution. And in this case, let me do the version for zero. Okay, the zero, that's the actual solution we got initially, right? Equals to cosine. Okay. So again, I'm gonna drag it. See how those diagonal lines are controlling the direction of those curves? Guess what those lines are? Those lines are lines of the form bx minus ay, the x minus 2y. If you solve for, so x minus 2y, let it equal to 0. So that's negative 2y equals to negative x, and y equals to 1/2 x. Okay, let me do an xy perspective. Isn't that the diagonal line y equals to 1/2 x, and also shifted up and down some units? How many units? The number of units that coincide with the maximum value attained for the surface. Now, those diagonal lines, guys, special name. Those are called characteristic curves. Yes, they're lines. They're straight lines, but they're in general called characteristic curves, which is actually what govern the behavior of the solutions to these PDEs, which in this case are different surfaces, different related, different curves related to it. Actually, there is another method of solutions to PDEs. It's called precisely the characteristic curve, which is a fancier version of what we're doing here, except that the method of solution, rather than changing the coordinates, which is what we did in this case, the characteristic curves method relies on solving a system of partial differential equations, which sounds crazy, but in a way, for some situations, it's easier than what we're doing here. So, okay, well, let me go back to the notes. Let's have a look at another example. Let's solve u with respect x plus 5 times the partial of u with respect y equals to 0, subject to the condition u of x 0 equals to 4e to the x. Now we're making the y coordinate equal to 0, not the x coordinate like we did before. I'm not going to do a graph for this one, but at least I would like to solve the problem. So let's see. So again, here just identify A equals to 3 and B equals to 5. That means the solution u of x, y equals to some function of 5x minus 3y, because B is the coefficient of x and A is the coefficient of y with an A. All right? Okay, so, and yes, that's the solution to the equation. That's the general solution only, right? The general solution only. Now, let's see. What about particular solution u of x 0 equals to f of 5x? Notice x remains the same. Y becomes a 0. That is minus 3 times 0. That is equal to some function of 5x. But what is that equal to? 4e to the x. Okay? But I don't want f of 5x. I want f of x. What should we do to get f of x? Divide by 5, right? Divide by 5. So 4e to the x over 5 equals f of x. Okay? All right. What do we do from here? Well, replace x with the characteristic line, the characteristic curve. Replace in every instance here. So that is now f of 5x minus 3y equals to 4 times e to the 1/5 times 5x minus 3y, okay, which is equal to, simplifying, 4 e to the x minus 3/5 y. So u of x, y, which is now the particular solution, not the general one, that'll be 4 e to the x minus 3/5 y. And you can take the necessary partial derivative. It should check the PDE on both sides. All right. I'm not going to show you a graph of this one. I don't have one, but I mean you could create one, I guess, using GeoGebra. I'd rather move on to the next topic. Okay. Here we go.